Okay, here we're going to work on writing the height, a function to calculate the height of a binary search tree in Racket. And we really want to be thinking about this using the natural recursive structure of a binary search tree. And we're going to take the perspective of a single BST node and think about ourselves as a single BST node as having a key and then a left and right subtree. Okay, here are some conceptual calls. So the height of a single node is 0. The height of something with 2 nodes is going to be 1. Height of an empty tree is going to be negative. And again, height is the length of the longest path from the root node to a leaf node. And you can imagine that we could have defined it as one different than that, like an empty is 0 instead, and that would just be one different than what we've decided. And we're just going to use this to be consistent. Okay, so we're going to take the perspective of an individual tree or an individual subtree. So if I'm an empty binary search tree, then I'm going to return -1. Otherwise, I'm going to ask my left subtree what its height is. And I'm going to ask my right subtree what its height is. I'm going to figure out which of those two things is taller. So which of those gave me a bigger number? So say my left subtree has a height of 10 and my right subtree has a height of 4. Then my eventual height is going to be 11 because it's the taller one, the 10, plus one more to count my individual node. All right, I want you to pause it here and try and write height that uses those helper functions for Racket binary search trees. So try and write the height function using those helper functions. And you can pause it here or on the next slide, I'll show you those helper functions. So here was a list of those helper functions. You might want to pause it here instead. Okay, so hopefully you paused it, but I'm going to come here and work on writing height in Racket. So remember, if I was an empty tree, if the tree was an empty tree, then I want to return -1. It's a little bit strange, but that was the height of an empty tree. Otherwise, I'm going to call height on my left tree, and I'm going to call height on my right tree, or my right subtree. I want to take the max of those two values, and then I'm going to add 1 to the max of those two values. So the most important thing here is to see this naturally recursive structure. I call height on my left tree, it gives me a number. I call height on my right tree, it gives me a number. I take the max of those two and I add 1. Probably this seems really similar to when we wrote length for a list. So I've added the code for length here, and it's got that similar structure. Instead, if it's empty, then I return 0. Okay, well, our empty tree was -1, and otherwise we add 1 to that recursive call. And just like we called rest in the length case to make the input that we were working with smaller in our recursive call, similarly left and right subtrees that we get by calling left tree and right tree, that means that we're going to make a recursive call with a smaller input, closer to the base case. And that's our goal when we're writing recursive code.